How do we represent data? We're going to be talking about data a lot in this class, and when you write down your data analysis, you'll want to be able to communicate it to other people. So it's important to know how to write about data in a way that makes it both compact but also understandable. So the first thing to keep in mind is how to write about data when you're writing about it in a text file, not in R code. Each data point is usually represented by a capital letter, and we try to make these letters representative when possible. So for example, you use a capital H for height or a capital W for weight. If there are more than one data point of the same type, we use subscripts. So for example, if we have three different people's heights, we might label them H with the subscript 1, H with the subscript 2, and H with the subscript 3. In general, when we're writing about the mathematics of data analysis, it might be more compact to write x sub 1 for height and x sub 2 for weight. If this is the case, then we need another subscript for the individual data point, for example, the height of different people. So we would add another subscript to the data point x and call it x sub 1, 1 for the height of the first person. You can imagine that you would then add a second subscript to the weight variable as well, so you would get x sub 2, 1 for the weight of the first person. Y is generally used to represent outcomes, and x is generally used to represent covariates. You don't have to pay too much attention to these conventions right now, but just keep them in the back of your mind for when we're talking about specific statistical methods later. In this course, whenever possible, we will try to use informative letters rather than the generic y and x. Next, we need to talk a little bit about randomness. We need to talk about randomness because most of the data that we will consider in this class will be data that varies from observation to observation or from person to person. And so we're going to let the variables x and y be called random variables because they represent the random observation that we haven't necessarily measured yet. In general, randomness is a very hard thing to define. Statisticians, probabilists, and philosophers have big debate about what is meant by random. In this class, we'll stick to a definition that a variable is random because it either represents an incompletely measured variable where we haven't measured the phenomenon completely to determinism, or because it represents a random draw from a population using a mechanism such as a random generator from a computer. Once we are talking about a specific value of a variable after we have measured it, then it isn't a random quantity anymore, and we will write those values with lowercase letters like little x and little y. We will write big X equals little x when we are fixing the random quantity x to be the observed fixed deterministic quantity little x. Similarly, we might write x equals 1 if we know that the measured value is 1. So we'll be using randomness to represent two different things. One, random draws from a population, but also to represent incomplete measurements of a phenomenon that might be deterministic if we had measured everything about it. As an example of this, we're going to talk about the coin flip. The coin flip is commonly used as the example or the highlighted example of randomness, but it can be modeled by deterministic equations. In this paper, Diaconis and his colleagues model a dynamical bias in the coin toss. They modeled the spinning of the coin as a dynamical system as it flies through the air, and they showed that a coin is more likely to land on the side that it started. Then they did experiments with extensive numbers of coin flips and demonstrated that there was actually a 51% chance that a coin flipped from a particular position will land in that same position. This shows that there's at least some determinism to the flipping of a coin, but some people have taken it even farther. So this is a link to a video produced by a person who created machines for flipping coins. One of the machines that he created is able to flip a coin so that 95% of the time it comes up tails. The machines are based on physical properties that if we had measured, it might be possible to always predict whether a coin comes up heads or tails. So we're using this random variable x to represent a coin flip only to represent our unmeasured knowledge about the physics of flipping coins. Now that we have defined random variables, we need to define distributions as a way of communicating succinctly the properties of those random variables. In statistical modeling, random variables like capital X are assumed to be samples from a distribution. A distribution tells us the possible values of x and the probabilities for each value. Probability is the chance something will happen, and we will abbreviate it in this class with capital P lowercase r. The probabilities must all be between 0 and 1, and the probabilities must add up to 1 in order for it to be called a distribution. As an example, let's flip a coin and allow capital letter X to represent whether it is heads or tails. X equals 1 if it is heads, and X equals 0 if it is tails. Since we haven't flipped the coin yet, X is still a random variable. We expect that about 50% of the time it will be heads, depending, of course, on whether it started off as heads or not. The distribution can then be written: the probability that X equals 1 is 0.5, and the probability that X equals 0 is 0.5. Since X can only take on these two values, the entire distribution is summarized by those two probability statements. There are two types of distributions: discrete distributions, which specify probabilities for discrete values, like a coin toss, and so these are usually used for qualitative variables. Variables can also take on all of the values 0, 1, 2, 3, and so on all the way up to infinity, as long as those values are discrete and not on a continuous scale. Continuous distributions, on the other hand, specify probabilities for ranges of values rather than for specific values themselves, and they're usually used for quantitative variables that are assumed to be measured on a continuous scale. However, even if we assume that a variable is quantitative, or we model it as quantitative, we might only see specific values. For example, you usually only see height reported in feet and inches in the United States, even though it could be measured at a much finer scale and be modeled as a quantitative variable. To understand distributions, or to describe them completely, we need a set of parameters. Parameters, for our purposes, will be considered to be fixed values that exist in either the population or under some assumptions. Parameters are sometimes represented by Greek letters like mu, sigma, or tau. Distributions are written as letters with the parameters in parentheses, like so. This is a normal mu sigma distribution. Similarly, we might see a Poisson distribution with parameter lambda. X tilde normal mu sigma means that X has the normal distribution. This is shorthand that will make it easier to write out specific equations that we need later on. There are three parameters that are considered by many to be the most important parameters in statistical modeling, although of course this is disputed. The mean of a random variable is the average of that random variable, and it's written as the expectation of X with a capital E. It stands for the expected value. We expect it because it measures the center of the distribution, or where most of the distribution is concentrated around. The variance of a random variable is written as var x, VAR. It measures how spread out a distribution is, and it's measured in units of x squared, where x is the random variable. The standard deviation is just the square root of the variance. It also measures how spread out a distribution is, but its measurement used in units of x, so sometimes it's more useful rather than in units of x squared, which might be less comparable to the expectation. If a variable has a higher expectation, then more often than not we will see high values of that random variable. If a variable has high variance, a random variable has high variance, then we expect to see values that are more and more spread out. Next we're going to talk about conditioning. Sometimes we may want to talk about a case where one of the random variables has been measured and observed and it has a specific value, and then determine how the other variables might be random around that particular value. So recall that when we use a capital letter like X, the value is considered to be random. The parameters, on the other hand, are considered to be fixed values. But sometimes we might want to talk about a case where one of the random variables is held fixed. To indicate what is fixed, we condition. So for example, X conditional on mu, written like this, means that X is a random variable with a fixed parameter mu. Similarly, we might condition on a random variable held at a fixed value. For example, y given x equals 2, written like this, means that y is the random variable y only in the cases where x is held fixed at 2. I'll show you an example of what this looks like in a minute. So now I'm going to give you a couple of examples of distributions. So one example is a binomial distribution. You can think of this as a distribution that describes the sum of a set of coin flips. So suppose you flip 10 coins and you count the number of times that they come up heads. And we assume that those coins are fair. The two parameters of the binomial distribution, n and p, represent the number of coins flipped and the probability that those coins come up heads. So for example, if you flip 10 coins and the probabilities are all fair, x is a binomial distribution with n equal to 10 and p equal to 0.5. This plot shows the values corresponding to the different number of heads that you might get from 0 to 10 and the probability that you get that number of heads. So for example, a value of 5 heads comes up about 25% of the time. Another example of a distribution is the normal distribution. Here, it's not a specific value that's being parameterized as a probability, but rather it's specifying probabilities for ranges of variables. So a normal distribution has two parameters, mu and sigma. Mu represents the mean of the distribution, and sigma represents the standard deviation. Remember that the mean of the distribution says something about where the center of the distribution is, and the standard deviation says something about the spread. So if x is a random variable that has distribution normal with mean 0 and standard deviation 1, this is what its probability density function looks like. The probability density function explains something about probabilities for ranges of the values of x. So we can calculate the probability that x will fall into a particular range of values by integrating under this curve. Something to keep in mind here is that we cannot calculate the probability of specific values using a continuous distribution. We can only calculate the ranges. So now let's look at one more distribution that's commonly used. This is a uniform distribution. The uniform distribution means that all values are equally likely. It's parameterized with two parameters alpha and beta, which are the boundaries of which values we consider to be equally likely. So in the case of a uniform distribution between 0 and 1, we're looking at any value between 0 and 1 being equally likely. And again, by summing up the area under this curve, we're able to identify what's the probability that x falls in any particular range. So now I'm going to talk a little bit about what happens when we change parameters. So again, this is a normal distribution, and it has parameters mu and sigma. In this particular case, we're considering the mean to be 0 and the standard deviation to be 1. It turns out, because of the way that the normal distribution is parameterized, the expectation of x is also equal to 0, and the variance of x is equal to 1. But if we change the parameters, then the expectation and the variance change, and so does what the distribution looks like. So in this case, we've left the mean to still be 0 and changed the standard deviation to be 5. This increased the variance to be 25, since the variance is equal to the standard deviation squared. Looking at the density function, we see that the density is much more spread out. It's still centered on 0, but the values are more likely at more extreme values. We can also change the mean of the normal random variable. So here we have a random variable with mean 5 and standard deviation 1. In this case, the expected value, or the mean value, is equal to 5, while the variance is equal to 1. Now, this distribution is shifted over from 0 to be centered at 5, but since the variance is only equal to 1, it's again a much skinnier distribution, which means that more values are more probable near the center, near 5. Another example of how you can change the parameters is the binomial distribution. So remember, we were looking at a binomial distribution that had parameters n equals 10 and p equals 0.5. This is equivalent to adding up the number of heads that you see in the flips of 10 fair coins. In this case, the expected number of heads, or the average number of heads, is equal to 5, which is just the number of flips times the probability of coming up heads. The variance is given by this formula, the number of heads times the probability times 1 minus the probability of heads. And this turns out to be 2.5. So in that case, we can change the parameters of the binomial distribution, for example, by making it more and more likely that the coins will come up heads. In this case, again, we flip 10 coins, but 0.8 of the time, or 80% of the time, the coin will come up heads. Here the expected value has changed because the number of coins times the probability equals 8. But also the variance has changed because by changing the probability, we've also changed the formula for the variance. And so the variance has actually gotten smaller. We can see that in the distribution because the values, the more and more of the values are large because the coins are more and more likely to be heads, but they're also being pushed up against the edge here, so they're more and more compact, making the variance smaller as well. There are very few distributions where changing the parameters specifically corresponds to changing the mean and the variance without some sort of interaction between the two of them. The normal distribution is one of those, and the binomial distribution is not. Now we'll take a look at what happens when we condition. So we're going to consider the case where y is a random variable that's normally distributed, and the mean of that random variable is another random variable, x. And the standard deviation is equal to 1. X is a random variable that's also normally distributed, and it has a mean of 0 and a variance of 1. So if we've observed and fixed x to be equal to 5, then we can say that y is a random variable with mean 5 and variance 1, which we saw before as a distribution centered at 5 with a relatively small spread. However, when we don't know what x is, then the distribution of y has to take into account the variability in x. Since the center of x is still at 0, the center of y will be at 0, and so the distribution is still centered at 0. But you can see that it's slightly more spread out if you compare this distribution to the distribution when we have a fixed mean. And the reason why is because this includes both the variability from y and the variability from x. So conditioning would remove some of that variability by assigning x to be a specific value. To learn more about these properties, you can see these two links to Wikipedia on the law of total variance and the law of total expectation. These plots are meant to illustrate these ideas. You don't need to pay too much attention to the specific mathematics unless you want to know about it, but it's good to know what we mean when we say conditioning, or what it means when we say that something has a distribution. If you want to learn more about specific distributions, you can go to Wikipedia and type those distributions' names into the search. Here's an example of the Poisson distribution. It shows you information about the distributions themselves, as well as information about their parameters, their means and variances, and other specifics that you might care to know. If you want to learn a lot more about representing data, or if you're very interested in the mathematics that underlie a lot of the ideas that we'll be talking about, Open Intro is a great place to start. This is a free statistics coursebook that starts from the very beginning and explains details about probability, distributions, parameters, and conditioning.